Okay, now we wish to combine these individual inequalities into one inequality, but if that's the case, now the delta i's that might be different for different i's, so we'll take the minimum of all delta i's so that we'll have a range where all the q inequalities simultaneously hold. Now set delta equal to the minimum of all delta i's, I from 1 to q. Now, let x be in E delta A intersection A. For this x, all these inequalities hold simultaneously. Now, let us consider f of x minus f of a minus. Now here, as we had in mind at the outset, now we wish to have the linear map there, which sends each u in Rp to this product. That's a linear map, and if this linear map satisfies the inequality in the definition of differentiability by uniqueness of derivatives, that will turn out to be equal to the derivative of itself. So we will have j sub f at A. So this matrix, u here, that will be x minus A. But in order, we'll use here, well, we will write this in terms of these expressions, but that means, well, this is what? This is a q vector. Well, the norm is, well, you take each component, square them, add them up, and then take the square root. But let's first consider the square of this. We can take the square root at the end instead of carrying that all the time with us. This is equal to the sum of, now the ith component of this. What's that? F sub I of x here minus f sub I of a here minus. This now is, this is a q by p matrix. This is a column matrix, p with p rows, p by 1. Well, so this product is a q vector, but its ith component is the ith row of this matrix. Take the matrix product of that with x minus a represented as a column matrix. But that will be, what is the ith row? Well, you have the ith coordinate function and its various derivatives. And the jth entry in this ith row, that will be multiplied with the jth entry of this vector, xj minus aj, from j1 to p. This squared. Because this is a real number now, well, it's absolute value, but we squared that, so the absolute value does not matter. So this from I equal to 1 to q. But this here is nothing but this dfia at x minus a. So this is equal to I from 1 to q fi x minus fi a minus dfi a at x minus a, the square of that. But the absolute value of this, well, that's less than or equal to epsilon over q times the norm of x minus a. So this is less than or equal to the sum from I equal 1 to q. Well, this inequality holds because x here is in b delta I of a, because delta is the smallest, so it's common to all of them. So this is epsilon square over q square, because we have the square of this. So the square of this is less than or equal to the square of this. X minus a squared this. But as you see, this expression in the sum, that's constant with respect to I. So you simply have q times the same thing. So you have this. Well, then this quantity is less than or equal to this quantity. Well, but then we can take the square root of both sides. They're all non-negative, getting this is less than or equal to epsilon over square root of q, and here x minus a, but q is a positive integer, so this will be less than or equal to epsilon x minus a, finally yielding the inequality that we wanted to show. So the function which sends each u to jfa times u, a matrix product, that linear map is the derivative of f at a. Okay. So if a function is differentiable on Rp to Rq, we can actually represent that in terms of partial derivatives. Differentiability implies existence of partial derivatives, but the converse is not true. But it would also be nice if we had a partial converse to that. The question then is, well, some information, but not just the existence of partial derivatives, concerning partial derivatives, would that actually suffice to conclude that f is differentiable at a given point? Well, there is some such converse, and it will be useful. We will have this theorem, but omit its proof. Again, you can see the proof in Bartle if you wish. Now, again, we have the same setup. We take an interior point of that. Now, if for each coordinate function and for each variable, the partial derivative of the coordinate function I with respect to xj. Well, existence at A, that does not suffice, exists on some neighborhood of A and is continuous at A, then f is differentiable at A. So in particular, if all these partial derivatives exist and continuous everywhere, well then the function will be differentiable everywhere. Okay. This will turn out to be useful in the sequel, but it is the time to note it, to observe it here. We will use it later. Now, as I promised, at the end of each chapter, we will have a theorem or result which will tell us what we have learned concerning optimization. What we have learned here, the summary of that and the proof of that, that will also tell us what to do next. That will take us to our next chapter. It will be a passage from here to the next chapter. Theorem. Again, a similar setup. But since we are interested in finding maxima, minima, and so on, we'll take our function to be real valued here. Well, we defined the derivative itself and differentiability at interior points, but when we defined the directional derivative, well, we did not require that it was at an interior point. Well, we just required that the point was a point in the domain and a cluster point of the domain. So, well, that will be useful here in getting this result. It will make it more general. Now, assume that now I'll take 2 points here. One will correspond to a maximizer, the other to a minimizer. X upper star, X lower star in A are cluster points of A. And let me write this in red. f of x star is, well, I can write here maximum. If I write supremum of f of a, that's equivalent because f of x star then will be a member of this. Let me write it. Makes no difference, but maybe it's more natural. And f of x lower star, that will be the minimum of f of a. Moreover, assume that U in Rp points into A at x upper star in the first case and at x lower star in the second case. Now first, if f sub u at x upper star exists, then what can you tell about f sub u of x star? Well, if f of x star is the maximum of f of a, if you move away from x star in whatever direction allowed, staying within A, you will be going downwards, downhill. So this will be less than or equal to 0. Well, if it comes to the minimum, well, if you're at the bottom, if you move away from that point, you will be going upwards, you will not go down. In the weak sense, it could be constant as well. In fact, this is the main result. It's simple, but we can now get from this the following. Now, if A is not A, x star is in A interior, x lower star is in A interior, and f is differentiable at x upper star, respectively at x lower star, then df at x star, that will be 0. Now, this means what? Df x star, that's a function. It's on Rp with values in Rq. So this stands for the 0 function here. That is, spelled out in detail, df of x star at u is equal to 0 for each u in Rp. It's the function which takes on the value 0 everywhere, not just the real number. And here, df of x star, that's the 0 function as well. The proof is simple, but let's go through it. It's telling. For the first part, I, Well, let's assume that the directional derivative of f at x star in the direction of u exists. Now what? Well, u points into A at x star. Well, that means there is some delta positive such that the line segment from x star to x star plus delta u, that entirely stays within cap A. Since u points into A at x star, there is some delta positive such that the line segment from x star to x star plus delta u is contained in A. Okay? Now we're doing it for the black version, but you'll see, well, the red version will be very similar to that, just one inequality will change, that's all. So, let me write it in this form. For all t, well, I will exclude 0, x star plus tu, this will be in A. This is what this means. Well, when t is equal to 0, that's true as well, but I'll be dividing by t, so let me, this much is enough. But what do we know? F of x star is the maximum of f of cap A. By hypothesis, f of x star is larger than or equal to f of x star plus tu. That is f of x star plus tu minus f of x star. That's less than or equal to 0, but t is positive. If I divide this by t, that is less than or equal to 0 as well for all t in 0 delta. Do we know anything about the limit of this expression as t tends to 0? Does it exist? Do we know that? Yes, f sub u of x star. We know that that exists. That's by hypothesis. So limit 1 over t f of x star plus tu minus f of x star as t tends to 0, that exists, and in fact it's f sub u of x star. But what does this imply? You have t for all t in here, that this is less than or equal to 0. Then this has to be less than or equal to 0 as well. One remark here. This is only for t's which are close to 0 from the right, from the positive side. But that makes no difference. We know the existence of this limit. And well, if this holds, when you approach t from 0, then it follows that the limit obeys this as well. You can just consider points which are larger than 0 and arbitrarily close to 0. Well, that will not guarantee the existence of a limit. If we just knew that this approached a limit when we allow t to approach to tend to 0 from the right, that would not guarantee the existence of the limit. But the existence of the limit, that's explicitly given to us. This just gives us what inequality the limit should obey. Yeah?
When we define the directional derivative, I mean, we didn't exclude the t cannot take negative.
Yeah, we did not.
But is it well defined? Because we say u points only in the positive directions to a. So we don't allow for delta?
No. I mean, we take all t in the delta ball about 0 such that a plus tu is in the domain, in cap A. If you go back to the definition runs as follows. Given epsilon, there should exist some delta positive such that for all x, in the punctuated delta ball, for all t, in the punctuated delta ball about 0, such that a plus tu is in cap A, then the norm of the difference, well, that should be less than epsilon. So sometimes, if that's a boundary point, it's a cluster point, not an interior point, well, t less than 0, that's irrelevant. I mean, that belongs to the punctuated delta ball about 0, but a plus tu will not be in cap A. So, but if it's an interior point, you can go both ways. So we have this. But when the red version is similar, well, the only thing will be that this will be reversed and the inequalities will be reversed everywhere. The rest is the same. Similar. So if I write it in red, it's clear that this refers to the red version. Okay, now, secondly, assume that x upper star is in A interior and f is differentiable at x star. Well, now, any u in RP will point into cap A at x star since it's an interior point. For any u in RP, u points into A, into cap A at x star as x star is in A interior. And f sub u of x star exists. If it's differentiable, all the directional derivatives exist. Now take any u. In RP. Now we have df of x star at u This is just f sub u of x star, but from the above we know this is less than or equal to 0. But minus u points into cap A at x star as well, because it's in RP as well. But also, the fx star at minus u, that is, well, let me just write this, but also f sub minus u of x star, that's less than or equal to 0 as well. Well, pictorially, you go in the direction of u, you go downhill, but you're at the top. Well, if you go just in the opposite direction, you go downhill as well. So that's what this means. But now, how are these related to each other? F minus ux star and f ux star. F minus ux star, that's equal to the f of x star at minus u. That's just our theorem, our last theorem last time. But what do we know about the fx star? It's linear. So this is equal to minus the fx star at u, since the fx star is linear. But this is minus f sub u of x star. So if this is less than or equal to 0, f sub u of x star is larger than or equal to 0. Thus, f sub u of x star larger than or equal to 0. Well, let me write it, although it's clear, since minus f sub u of x star is less than or equal to 0. But now, combining these two, hence, f sub u of x star is equal to 0 for all u in RP. That is, d of f of x star of u is equal to 0 for all u in RP, which was to be shown. Well, from calculus, we know very well that the converse is not true. From the one-dimensional case, well, the derivative might be equal to 0, in which case, as a linear map, it will be the 0 function as well. But that may not correspond to either a maximum or a minimum. Well, then, the natural next question is, can we actually impose some further conditions on the family of functions we consider, such that the converse will also be true? For what kind of functions do we have the converse? That is, if well, for the one-dimensional case, if f prime x is equal to 0 and f satisfies such and such a condition, that implying that f is actually attains its maximum, or a local maximum, but some maximum at that point. What kind of functions? Well, for maxima, concave functions. For minima, convex functions. So, well, then, it is only natural to consider hereafter concave and convex functions, well, because for optimization results, well, the converse of this will also be true. Of course, we'll concave and differentiable and so on, but differentiable at the point where this happens, okay? If it's not differentiable at some points, well, then that might lead to some problem. I mean, it will not, you cannot obtain it from here. But before going to that, now let me again consider an example. For the first part of this optimization theorem, well, X star is in the domain, but it's a cluster point, not necessarily an interior point. Okay? Now, let us consider this function on the interval AB, closed interval, real valued. Suppose it's this. Does it apply to this point, that theorem? Well, A is in the domain. It's a cluster point of the domain. The function attains its maximum at this point, so that's X upper star. Does, well, 1, for example, the vector 1, the real number 1, that's the vector here, that points into the domain at A. Well, so the directional derivative of f at A in the direction of 1, that has to be less than or equal to 0. But the directional derivative in the one-dimensional case, in the direction of 1, that's nothing but the derivative itself. And that's, the slope is negative there, so it's less than or equal to 0. But what about this? Does it apply to this point? B is a point in the domain. It's a cluster point of the domain. The function attains its maximum at B. Now, 1 does not point into the set in this case, but -1 does. So the directional derivative of f at B in the direction of -1, that should be less than or equal to 0. But when you take its directional derivative in the direction of -1, what you're doing is you trace the function from right to left. So the slope, although if you trace it from left to right, is positive, it's negative. So here, you don't need to, well, as in calculus, you usually do, you don't need to distinguish between points which are interior or which are just non-interior cluster points. Okay, well, that happens, well, this is just a one-dimensional version, but you can extend this to higher dimensions as well. So this adds something. Here, I will just give you, I will not start with convex and concave functions, but will you give a pictorial agenda of the next chapter? Here, this is a typically concave function on R to R, and this is a typically convex function. Now we will consider for concave as well as dual convex functions 5 different characterizations. Now, one test for concavity is you take 2 points on the graph, you form the secant. Each such secant should lie below the graph. In fact, the standard definition of concave functions is just the formalization of this observation. Here, the other way around. This requires no differentiation, nothing further than just the function itself. The second observation, what can you tell about this region under the graph if the function is concave? This will be a convex subset of R2. While the upper part, what stays above the graph in a convex function case, that will be a convex subset of R cross R. So that's the second. The third one that requires differentiation and differentiability, you take any point here and you form the tangent line. The tangent line should stay entirely above the graph, while here, if it's differentiable at the point, the tangent line will stay below the graph all the time. If it's differentiable not just at a particular point, but everywhere, then here, that will be less than or equal to 0, because the slope, that will be non-increasing. If it's decreasing, then this will be strictly concave. So this will be f prime non-increasing. Here, it will get larger and larger, f prime non-decreasing. But if it's twice differentiable, then f double prime, that should be less than or equal to 0, and f double prime larger than or equal to 0. So here we have, in terms of secants, in terms of the subgraph and the epigraph, that's 2. Here, the tangential lines, the position of them, that's 3. F prime, non-increasing, non-decreasing, that's 4, and this is 5. What is the most general mathematical construct that allows the notion of a convex set? In this course, just. Well, the definition of a convex set is if x and y belong to the set, and lambda is, say, a non-negative number less than or equal to 1, lambda x plus 1 minus lambda y, that should be in the set again for each x and y and for each lambda in the unit interval. What do we need there? Just scalar multiplication, lambda x, 1 minus lambda y, and vector addition. we'll take the first two characterizations for real valued functions defined on a real vector space, because we don't need anything further than that. But when we come to the third characterization, that requires differentiation. So we'll do it in Euclidean spaces, the third characterization. The fourth one, that actually, well, we know f prime, if f is on R to R, f prime is on R to R as well. And then we can say what's increasing, what's decreasing, non-increasing, non-decreasing. But the derivative in the generalized case, it's a function. Well, how can we compare two functions, df at A and df at B? Well, whether one is larger than, so there we need to extend the notion of being monotonic. And for this, we will need introducing, we have just the first order derivative, dfa. We will extend that to higher order derivatives. So we'll add to our chapter on differentiation here as well, but we will introduce all the notions when we need them. But this is just the agenda of these 5 characterizations that they will make up our next chapter. And of course, we will again wrap up by asking, well, what have we learned concerning optimization? So, well, then we'll have something small in addition to that for this semester, but that's almost all.